Howdy, today on Flipping Science we're looking at electrolytic cells. So the science understanding we're going to look at: electrolytic cells are used to produce required substances, identify the anode, cathode, their charges, as well as the direction of ion and electron flow in an electrolytic cell given sufficient information, and write electrode half equations for an electrolytic cell given sufficient information. In electrolytic cells, energy is used to force electrons in the opposite direction that they would normally go. So in the non-spontaneous redox direction, the electrons going in the opposite direction. What that means is that things would normally oxidize are instead reduced, and things that are normally reduced are then oxidized. So we're forcing the electrons in the opposite direction. We can use electrolysis for a few things. We can use it to plate metals onto other metals, or metals onto anything that conducts electricity. We can make active metals from their ions, and we can also make gases from liquids, for example. You can use electrolysis to break up water into hydrogen and oxygen. And that tells us where the name comes from. So electro for electricity, lytic, lysis is breaking, so breaking using electricity. So here's an example electrolytic cell. So we've got a copper sulfate solution down the bottom here, 2 copper electrodes, and we've got a source of electrons being forced in the other way. So this is a battery up here. So we're forcing the electrons in this direction over here. So we're forcing them over to this electrode. And at that electrode, we're getting copper ions from the solution plating onto the copper electrode that's in the solution. So because we've got the ions being reduced to copper, so the copper ions are being reduced to copper, that's happening at the cathode. So cathode is where reduction happens. And because we're pushing the electrons over here, we get a lot of electrons on this electrode, that's giving it a negative charge. If we have a look at what's happening at the other electrode, so this is going to be the anode, copper from the rod is being oxidized to copper ions. So the copper is being oxidized to copper ions, they're sitting in solution, and then some of those copper ions will be reduced onto the copper rod. You could use this to plate something in copper, so rather than having a copper rod in here, you could have a graphite sheet, a graphite rod. You could have another metal, so you could have a key and you could coat that key in copper, for example. Here's another example. So here we have making sodium. So here you have a molten sodium mix. So this is just salt that's being heated up. It has to be molten, not a solution, because the solution won't work. You'd reduce water rather than the sodium. So at the cathode, again, we're getting reduction. The sodium ions from the melt are being reduced to liquid sodium. The liquid sodium would go up in this case because it's less dense than the salt. So you could collect it at the top over here. And the chloride ions over here would be oxidized, so their oxidation is lost. The chloride ions lose their electrons and you make chlorine gas. So chlorine gas would be bubbling up over here. So this is how you make active metals from their salts. So you can use this to make sodium, potassium, lithium, and so on. Some things to remember from those diagrams we saw. In an electrolytic cell, the anode is always the side of oxidation and the cathode is always the side of reduction. That's the same for electrolytic or galvanic cells. What changes though is the signs. So because we're forcing the electrons in the opposite direction, what would normally be anode negative oxidation for a galvanic cell becomes anode positive oxidation. And over the other side, what would normally be cathode positive reduction becomes cathode negative reduction. So you can still use your mnemonics from the galvanics to help you remember, but you just have to remember that the charge changes over. So in an electrolytic cell, the charge is reversed compared to the galvanic cell. So we'll just go through a bit more detail of how we can refine other metals other than active metals. So copper is a good example of a metal that's refined using an electrolytic cell. So they make some impure copper first from the copper ore. So that's impure copper. It's normally about 95% pure, so there's other impurities, there's slag, there might be gold, and there might be silver in there too. So by refining it this way, you can collect some valuable metals. So that the anodes, and at the anodes the copper gets oxidized, and both of the electrodes are placed in a copper sulfate solution. So as the copper is oxidized, you get more copper ions in the solution, and then over the other side you get the copper being reduced. So the copper ions from the solution are reduced to pure copper metal, and they're usually plated on a pure copper cathode, and that is what can be sold. So you sell the copper cathodes because they have 99.999-ish% pure copper. So here's a picture of what would happen. So here you have your impure copper, blister copper anode, so it's not very pure. That's being oxidized to copper ions in the solution. And when that happens, any less reactive metals like silver and gold, they form a little pile underneath here. That's called anode mud, and that can be quite valuable to recover. The copper ions go into solution, and then they are reduced over at the cathode. The copper ions are reduced to pure copper. So here we can see, a very old photo, we can see some of these sheets. So this is pure copper here. So these are pure copper cathodes that are dangling in the solution. And that's, like I said, you take those out, you cut off the ends, and then that's what you sell. So here's an example question. It says, during the electrolysis of molten potassium iodide using graphite electrodes, potassium metal is produced at the cathode and iodine gas at the anode. Write an equation, state the advantage of using graphite as your electrodes, write an overall equation, and state at which electrode oxidation occurs. So let's break that up a little bit. So the first part of the question says, write an equation for what's occurring at each electrode. So at the cathode, okay, we're going to get reduction of the potassium metal. So potassium ions are going to be reduced, so K+, we need 1 electron, and that's going to produce potassium. Now that'd be liquid. Potassium over here we'll call the potassium ions. They're not in solution either, so we'll just call them liquid too. So at the other side, at the anode, we're making iodine gas. So the iodide ions are going to, and we're going to need 2 of those. They're giving up their electrons because they're being oxidized. So they're being oxidized to iodine, and that's a gas. So again, they're molten in there, so we call that liquid, and we need to have our 2 electrons on that side. So state the advantage of using graphite electrodes. Graphite electrodes, they conduct electricity, but they won't react necessarily. They're not going to react with the potassium or the iodine gas. So they're inert, they don't react, but they can still conduct electricity. Write an overall equation for the reaction. So what we need to do is add our 2 half equations over here. So I need to double everything that's with my potassium. So I'm going to have, so it's going to be 2K plus 2I minus goes to 2K plus I2. So all I'm doing is doubling what I had for my cathode reaction, and I'm just going to add that to my anode reaction and cancel out the electrons, because they should cancel out from both sides. So the last question says, state at which electrode oxidation occurs. Oxidation occurs at the anode. Another question says, draw a diagram of an electrolytic cell which would be suitable for plating a nickel chain with silver, using silver nitrate as the electrode. So I've got a set up one over here, so let's label this. So I'm going to start on this side. We're going to, so we're plating, so I'm going to call this, so this is going to be a silver rod. I'm going to pop that in the solution. Down here we've got silver nitrate, AgNO3 solution, aqueous. So down here we've got silver nitrate. That means this is going to be my nickel chain. It doesn't look much like a chain, but we get the idea. Okay. We're going to label some things. So this is going to be our anode over here. Anode is going to be positive in this case. Over here, the nickel chain is going to be negative. It's going to be the cathode. And so what's happening is the silver ions from the solution will plate onto the nickel chain. So they'll come out of solution, they'll be reduced. Silver ions are reduced to silver on the surface of the nickel chain. We might plot in the direction of the electron flow. So the electrons are moving in this direction. So they're moving from positive to negative, which is the reverse of what they would normally do. We're shoving in energy, so they're pushing in the non-spontaneous direction. What else do we need? That's probably about it. We could write down the equations for what's happening as well. So at the anode, we're getting oxidation. So the solid silver is going to silver ions plus an electron. So that's oxidation. So we'll write the equation on the other side as well. So over here, silver ions are being reduced. So we've got silver ion in solution is gaining an electron, and we're reducing that to silver metal. That's an S, believe it or not. We're reducing that silver metal on the nickel chain down here. So the nickel chain in solution is going to be plated with silver from the solution. So today we looked at electrolytic cells and looked at some example questions. That's it for Flipping Science today. See ya.